So it's the 28th. Moving right along here. Are you guys all dressing up for Halloween?
Yeah.
No. I'm going to dress up like a math teacher.
I'm gonna dress up as a Riley Smith.
Thank you, Rain. It was very nice.
I'm gonna dress up as a
Pretty
Riley Smith.
good.
So again, I want to stress that on the other side of this, there's a whole lot that we're not going to talk about right now. We talk more about it next year and in other classes. But the other type that we will eventually talk about is exponential. But today, again, I want to stress all we're interested in is do you make a straight line? Or don't you? If the answer is you don't, I don't care what it is. I'm just going to say it's not a straight line. So this is the only part of today's notes that I don't want you to write down. So you would agree that if I put some points like this, like if someone gave me some data and I graphed the points on a piece of graph paper, you would agree that that's nonlinear, correct? Because yeah, three of them look like they might be linear there, but then this fourth one went rogue and it kind of looks like a broken bone there. So that is non-linear data. However, to be linear, if I took this one up and I put him kind of in line with the others, then I might be able to say, yeah, that looks like pretty linear data to me. So we're going to be doing this today just without the assistance of graph paper. We're not going to be plotting points and looking for, straight lines, literally speaking. We're going to do it mathematically. And what we're going to be studying today is called rate of change. You've seen rate of change before. You've probably seen it at a couple different instances in your math career before you met me. I'm guessing that last year in 8th grade math with Mr. Manlove, you used this word a lot. Is that a pretty safe assumption? Slope?
Yes.
Yeah.
Good. So really, I'm going to try to not keep saying the word slope. It's just going to come up a couple more times here while I talk myself out of it. But as we go through today, I want you to understand that when we do our rates of change, really all we're finding is the slope. We're just not going to address it explicitly as the slope. We're going to call it rate of change. So rate of change is defined in math, generally speaking, as how much something changes divided by how long it takes for it to change. We will come to know that as delta y over delta x. Does anyone know what delta means in Greek? Very good. Change. So when we study delta y over delta x, it's a simple concept. It's how much is y changing divided by how much is x changing, right?
Right.
Delta y is change in y. I'll write that down here off to the side for you so that this isn't. So when you look back at this Sunday, you'll be like, oh, that's what that means. I forgot. Remember, delta y means change in y. And then delta x, of course, means change in x. So we're going to study today how does delta y delta x tell us if points are in a straight line or not. Clearly, if you go from one point to another point and the delta y over delta x comes out to 2/3, that means y is changing by 2 and x is changing by 3. If you go to the next pair of points and you get a delta y over delta x of like negative 2/3, clearly that's not a good example, like 3/4, then the slopes or the rates of change are not the same. So the data wouldn't be linear. So let me show you now examples of what you're learning today. And I took this whole assignment, this one day, this lecture, the assignment, every little bit of it, I pulled right off your next district assessment. There's an entire problem dedicated to this at the very end of your Unit 2 district assessment. And the instructions are going to say this. And if you don't want to copy it down, I understand, but this is what the directions will say. And I'm gonna type it right up here, just like you're gonna see it on the text. So the directions are going to say create an XY table. And determine if the relation is linear or nonlinear. So this is what the directions are going to say. I'm going to scroll this up a little bit. Oh, I meant to say determine if the relation, not in the relation. I'm guessing you guys figured that out. My bad. One of those days. There we go. All right. So I have 4 examples of this, and I'll try once you see that there's not a lot of trickiness going on here. Hopefully you feel like A, I learned, I understand, and B, this isn't that difficult. So in our first example, I'm going to give you some X and Y values. And we're going to determine if the points are in a straight line or if they're not. And we're going to do it without ever graphing the points. So for our first example, we have 2, 4, 4, 7, 8, 13, and 14, 22. So the goal is to see, is this linear data? And to be linear, that means that your Y has to be changing by a constant amount, not a percentage. Like if something goes up by 50%, that's not linear, because 50% of what you have this week is more than 50% of what you had last week. So if you want to see linear data, then the amount that you change by should be the same every single time. So in order to do this, step 1, we're going to follow the directions. This is, I kind of failed at this last hour. We're going to make a table. And I think you guys have probably all made these tables before, but generally people just make their tables like this. X goes here, and Y goes here, like this. And which numbers are we going to put down the left-hand side? What will they say? Nice. 2, 4, 8, and 14. Right? We know that with ordered pairs, every ordered pair is an X and then a Y. And then the other numbers, the Y coordinates, are going to go down the right-hand side. So we're going to go 4 and 7 and 13 and 22, like this. Now, the goal, don't mind the buzzing phone, it'll stop soon. So the goal here is to see if I had graph paper, if we were doing this visually, I would graph the first 2 points and find their slope. But what we're going to do is just find delta y divided by delta x. And we have to do it for every pair of consecutive points. So I'm going to start with these 2 that I'm bracketing in yellow. That's just 2 points, right? So remember, go back to the top of the notes, delta y divided by delta x. What is delta y in this particular case? Yeah, Cody. It is 3. Delta y means literally change in y. And if you kind of look where I'm moving my pen right now, you would agree that for 4 to become 7 is an increase of 3. So our delta y value is positive 3. Now we're going to stick with the same 2 points, but we're going to go to the other side, the x side, and ask ourselves, how much does 2 have to change to become 4? And the answer is 2. So our first rate of change is 3/2. That doesn't mean anything. It won't mean anything until we have found more, because what we want to look for is now between every pair of points, does the rate of change stay the same? So I'm going to switch colors now, and I'm going to bracket these 2 right here. And we're going to do the same thing, rinse and repeat, delta y over delta x. What is delta y for this pair? How much
6.
does, 7 has to go up by 6 to become 13. So our delta y is 6. What's our delta x? Yeah, 4 goes up by 4 to become 8. Is 6 over 4 the same rate as 3 over 2? It is, because if you reduce it, it's the same. Selling 6 things in 4 hours is exactly the same rate as selling 3 things in 2 hours. Okay? So far we're matching, but we can't stop yet. This goes back to the drawing that I did at the beginning of the lesson, and that is that, you might have 3 points in a line, but the 4th could go rogue. So we need to go, again, round 3. And this time we're going to do the points that are bracketed in purple. What is delta y? 9. 13 goes up by 9 to become 22. What's delta x? Is 9 over 6 the same rate of change as 3 over 2?
Yes.
It is. If you reduce the fraction, divide them both by 3, what we see is these all have a constant rate of change. To go from any piece of data to the next, you have to have a change of 3 for the y's and 2 for the x's, or some multiple thereof. So we would agree then that this is linear data. Now, the way we justify our answer is we just simply say, yes, it is linear because the rate of change is constant. Okay. Does that make any sense at all? Again, translation, if we graphed them, what would they look like? A straight line. Yep. And we'll talk much more about straight lines and slopes in the next unit. But for today, just trying to avoid that, just want you to kind of have that in the back of your mind. If the data is linear, then the points form a straight line. Okay, the amount that we change by per unit of time never changes. Let's do another one. Okay, so for this one, our points are going to be -6, 7. And what I'll do is for the last two examples, I won't make you, I'm not going to give them to you like this. I'll just put them straight into a table form because we have to always do this table form. So I'll save you a little bit of time on the last couple. But for this one, let's do one more. So here they are in their ordered pair format. Same instructions will apply. We're going to turn them into a table and look at the rate of change. I'm really trying to teach this better this year. I've been really bad about teaching this in the past. And so I'll just show you quickly the trouble I've had with this. And I think where I have failed my students is in teaching it like this. You don't have to write this one down. I'm just showing you kind of where I've been in the past. Like if you know anything about this concept at all, you could look right at that and say that this is linear data. And the thing about it, what I'm trying to avoid is making it too simple for you. Do you see how X's go from 1 to 2 to 3 to 4? And then do you see how the Y's then go down by the same amount? Look, down 1, down 1, down 1. You could look at this really quickly and say that that's linear data, right? I wanted to avoid that. That's been my mistake in the past, was like insulting the intelligence of my students. So that's why today's numbers, I'm trying to be a little bit more creative with making you hopefully not just be able to look at this. Some of you might already be able to, but ideally I want you not just to look at it and go, yeah, it's linear, or no, it's not. But the more the better you get at this, eventually you can just look at them and figure them out. Anyhow, let's make a table. So we're going to do X's on the left, Y's on the right. And what numbers are going to go down the left-hand side?
6, -3, 0, 9.
Nice. And then down the right-hand side?
7, 6, 5, -.
So now we're just going to go and we're going to find the rate of change for every consecutive pair of points. And so once again, I'll just bracket these two. What is delta Y? -1. What is delta X? +3. That one does not even need reducing. It's just that is a rate of change of -1/3. Done. Okay. You want to write this down? Okay, that's fine. Let's bracket these 2 points right here. What are these ones? What's the delta Y for those ones? -1. And what's the delta X? So far, we're looking pretty good, right? So let's do it again for the purple brackets right here. These 2 points, the last two. What is delta Y? -16. And what is delta X? +9. Are those the same? Could you reduce -16/9 and would it become -1/3? The answer is no. Therefore, these are not linear. This would be an example where you'd have 3 dots in a row, nice and agreeable, and then the fourth one would go out rogue someplace else. So this time we're going to say that the data is non-linear, comma, because the rate of change is not constant. To be linear, that rate of change has to stay constant throughout the entire relation. It can't change even a little bit at any point in time. All right, let's do a couple more. But again, this time I'm not going to do the first step. I'm just going to put it right in. You could just copy the table right off the board. So for this next one,
Is it constant?
Yeah, it's not constant. So this one, our X column is going to go 4, 1, 0, -4. And then our Y column is going to go -6, -3, -2, and +2. Again, I'm trying to bracket them for you. I hope you're kind of embracing that when you take your notes. What is my first pairings delta Y going to be?
3.
+3. Good job. -6 goes up by 3 to become -3. And then how does 4 become 1?
-3.
It goes -3. That one can and should be reduced. So the overall rate of change is what? -1. So now the hope throughout this problem is, will all the other rates of change match that? If any one of them doesn't match, then we got to say nonlinear. So let's keep going. We'll go with the yellow ones here. What is delta Y? Up 1. Good job. And then what is delta X? -1, because it gets smaller by 1. And 1 divided by -1, it matches -1. We're 2 for 2. But again, like we saw in that second example, the fourth point can go rogue. So we have to verify that they're all behaving correctly. So we're going to do these two. What is delta Y?
1.
It is 4. For -2 to go to 2 it's an increase of 4. And what is delta X? And what does that equal? So on this one, we would say linear, because yes, very good, Mia. It's linear because the rate of change stays constant. Any questions so far?
Hold on, I'm confused.
Last one? They're all -1s. Yes, correct. Last one, and then I'll let you get started on your assignment. For our X column, we're going to have -2, 1, 3, and 5. And then in our Y column, we're going to have -8, -11, -3, 13. So pair by pair we go, right? We check first point to second, we check second to third, we check third to fourth. If they all behave, then we know what to do. So here we go. What is delta Y for the first pair?
-4.
Good job. It goes down 3. What is delta X? Goes up by 3. So just like last problem, we see a rate of change of -1. Then we're going to do the second pair of points right here. Delta Y goes up by 8. Delta X.
Down by 2.
For 1 to become 3, last I checked, is an increase of 2. And 8 reduces by 2. 8 divided by 2 is 4. I wanted to get this example in here for you to show you that we no longer even need to do the last one. If I were to draw these purple brackets, I would be wasting my time, because I've already figured out that just within the first 3 points, they're not in a straight line. So I don't need to go to the fourth one, and I could say it's nonlinear. I already found a change in the rate of change. And it can happen early or it can happen late. Like, you'll know by the time you get to the third point if you should carry on, press on, or if you should just phone it in at that point. So I will say this before I stop the recording, that when I wrote this assignment yesterday, I tried a different approach to writing these problems, because honestly, I had to try to stay creative to write 13 problems. Why 13? I just thought it fit nice on the paper. Sorry. But when I was writing them, I tried a different method, and I think it backfired. I'm just going to warn you right now. I hope you're still listening. You're going to find that a lot of the problems on the assignment you're about to do are nonlinear. So I don't want you to think you're doing something wrong if you find that the vast majority are nonlinear. Bless you. When I wrote it, I meant for about half and half split. I did not get that. I got lots of nonlinears, and a few linears. Got it? Okay, so your assignment is on Canvas. It's just a normal thing. Clicky to PDF and do it on your own paper. For each one, you make a table, and then you do what we did. I will tell you what I told third hour. For those of you listening, if you want to stop making the tables at any point, you can just for this assignment because it gets kind of boring. But on the test next week, you have to make the table. So that's why I put it in the instructions. But if you get to like number 5 and you're like, man, I'm so sick of making the XY table, you can still do these without the table. Just don't do that on the test. Okay.
Mr.
Yeah.
You have a computer.
I do.